Good afternoon, everyone. 大家下午好. So thanks, Professor Shen, for the very inspiring talk. It's really a great honor to be able to share also our research into Delft that we did on IBC solar cells. So today I will present a work from our PhD student, Katerina Kovacevic, about simplified processing of novel IBC silicon heterojunction solar cells with molybdenum oxide blanket layer. And in this talk, we will focus on modulated surface texturing for improved light encoupling. So front-back contact silicon heterojunction solar cells has already demonstrated efficiency over 27%, and this is mainly thanks to its excellent surface passivation. And this efficiency is further boosted to well above 27% in the IBC configuration, and mainly due to the improved light encoupling. And in typical IBC solar cell design, which has both N-type and P-type contact needs to be patterned, that result in a relatively lengthy fabrication process. And to simplify this fabrication process, an alternative concept, so-called the Turner IBC, that features a deposition of a full area P-type nanocrystalline silicon layer on a pre-patterned nanocrystalline silicon layer that's used as forming a Turner junction to collect electrons through the N and P layer, while the holes on the other side. And this one could enable simpler fabrication process. But however, due to the high natural conductivity of the P-type nanocrystalline silicon layer, it might reduce the shunt resistance of such devices. And in our group, we propose, instead of using P-type nanocrystalline silicon layer, we replace it with a full blanket layer of molybdenum oxide of a thickness of 1.7 nanometer. And in this case, it also features simpler fabrication process, and also thanks to the low lateral conductivity of molybdenum oxide, it also enables the device featuring higher shunt resistance. So now let's take a closer look at this device. So in this device, we have on the front side intrinsic morph-silicon passivating layer, and then a very transparent N-type nanosilicon oxide front surface field layer, and then on top, silicon oxide anti-reflecting coating. While on the rear side, we also have intrinsic morph-silicon passivating layer on the full area, and then a deposited nanocrystalline silicon layer and pattern it, and then on top, we deposit full area molybdenum oxide layer. And in between, before the deposition of molybdenum oxide layer, we also apply a plasma treatment that enable the molybdenum oxide eventually to feature proper high work function and also sufficient oxygen content in the material. And then we finish the device with the TCO and then metallization. And in this type of IBC solar cells, the holes are collected through the typical dopant-free contact based on molybdenum oxide. And with this contact stack already evaluated in the front-back contacted design, having a certified efficiency of 23.83%. While the electrons are collected through a low-vol contact stack that consists of intrinsic layer, N-type nanocrystalline silicon layer, and molybdenum oxide layers, and eventually the TCO and metal. And if we take a closer look at the band diagram of such a contact stack, and when electron holes are generated in the silicon bulk, the electrons can be collected, be transported to the intrinsic layer and N-type nanocrystalline silicon layer, while the electrons reaching the interface with the molybdenum oxide, it can be either tunneled through or through a thermoionic emission to the molybdenum oxide layer and eventually transported to the TCO layers. So unlike the Turner IBC that involves a Turner recombination junction, and in this case, all the electron transport happens through the conduction band, so there is no recombination process happening, unlike the Turner IBC. And with this IBC design, we can reduce the number of patterning steps, and also enable, and also we have a faster process of molybdenum oxide because it's only 1.7 nanometer, either via sputtering or evaporation, and then also featuring high shunt resistance. And last year in Zhuhai, I presented such a device with the efficiency of 21%. And after some optimization by the student this year, we could achieve efficiency jump of 2% absolute to 23.59%. And with relatively good VOC, because we are using a 280 micrometer thick float zone wafer. But as you can see, and also this device features copper-plated electrode. But as you can see, the JSA of such device is still quite below the state-of-the-art back-contact solar cells. So let's take a closer look at the optical analysis of such a device. So here we show on the slides the EQE and also Y minus the reflectance curves. So as highlighted in pink, those are the optical losses that accounts for around 5.9 milliamp per square centimeter. And the lighter pink accounts for the parasitic absorption loss that is around 3 milliamp per square centimeter. And also the cell features relatively high broadband reflection loss that is also around 2.8 milliamp per square centimeter. And therefore, it's very important for us to further optimize this device by focusing on the front-side optical management. And front-side optical management that is important because we have to ensure that it's being transparent while being featuring minimized reflectivity while without compromising the passivation quality. So firstly, we address the parasitic absorption loss. So in this case, we removed the front surface field layer, the N-type nanosilicon oxide layers, and also we tried to minimize the intrinsic layers on the front side. And according to our simulation, this could lead to a parasitic loss reduction of around 1 milliamp per square centimeter. And experimentally, with such simplified front side structure, we also demonstrate implied VUC above 745 millivolts. And next, let's address the high broadband reflection. So in this case, we have a reflection loss that is around 2.8. And then it's very natural that people think of optimizing refracting index grading. So basically, in this, instead of the simple silicon oxide layer as the anti-reflecting coating layer, so we built a double-layer anti-reflecting coating combining the silicon nitride and the silicon oxide form a better refracting index grading. And in this case, this double-layer anti-reflecting coating can still exhibit the morphology of the standard texture silicon. And with this double-layer anti-reflecting coating, we can see from the 1 minus reflectance curve a much better improved reflectance behavior of such device, especially in the middle wavelength range. And this leads to around 0.7 milliamp per square centimeter reduction of the reflectance loss. However, if you look closely at the shorter wavelengths below 600 or below 500 nanometer, this device still features relatively high reflection losses in the shorter wavelength range. So to address this, so on top of the double-layer anti-reflecting coating here, we added on top a porous silicon oxide layers that is formed via a cyanine poor plasma and then treated with some HF etching afterwards. And with such a structure, we could have a better minimized reflection loss in the shorter wavelength range. And this leads to even further reduced total reflection loss to 1.76 milliamp per square centimeter. So with this structure of such a modulated surface texturing, we are also wondering if this surface morphology also affects the angular reflectance of such structure. So with this, we applied angular intensity distribution measurement in reflectance. So here, you have incoming light, and then you also have a moving detector. So basically, we place the sample by tilting at the proper angle. Then you can use the detector to detect the perpendicular reflectance and up to the parallel reflectance from the substrate, so with a varying angle. And with this, we will show later the measurements of the reflectance from varying from 0 degrees to 90 degrees. So if we look again at the 1 minus R curves of the double-layer anti-reflecting coating only layer and also the one with additional porous silicon oxide, and we select the measurement at 400 nanometer for this angular intensity distribution reflectance measurements. So on the right, top right, you can see on the x-axis the scattering angle, and on the y-axis is the AID in the reflectance. So as you can see, apart from generally lower reflectance for those ones with the porous silicon oxide, but it also shows more even distribution or less angle-dependent reflectance when the device featuring such a porous silicon oxide modulated surface texturing. And further, when we look at reflectance, the wavelengths at 500 nanometer, where both curves shows nearly similar reflectance, but we can still see, in general, lower reflectance for the one featuring the MST, but also evener distribution of the reflectance, which means with such a structure, it can also enable probably better low light generation in the practical situation. So we implemented such an optical design into the device, and as a reference, that is 23.59% efficiency solar cell on the left. That had a current of around average, slightly below 40 milliamp per square centimeter. But the best-to-best device, after implementing such an optical design, we could boost the average JSC and the best JSC to over 41.5 milliamp per square centimeter. So in conclusion, so here I presented a low-vol IBC silicon heterojunction solar cells with molybdenum oxide blanket layer, which features simpler fabrication, faster processing, and also high shunt resistance. And also I presented a double-layer anti-reflecting coating plus a silicon oxide modulated surface texturing to optimize the light incoupling. And this reduced reflectance cross extended range of wavelengths and also angles. And last but not least, we showed the best-to-best more than 1 milliamp per square centimeter JST gain with such an optical design. So with this, I'd like to thank you for your attention.